Okay, guys, I'm very glad here to say that the OpenCAPI Acceleration Framework is finally online and you can check it out today. Actually, Pengfei and me just pushed that GitHub yesterday night. And I'm excited to see that Mattis, and he already submitted the first pull request, and I'm going to approve it and merge the request. And thank you. Okay. So I have seen, I'm very glad to stand here because I have seen so many people and had worked on CAPI Snap. And so, they have seen the development work on CAPI 2.0, and today we will have a look at the things, where it goes, and what improvements we have made for OpenCAPI. Okay, so today I will introduce a little bit. I think maybe I can be quickly to deep into a little more details about the OC-Accel itself. So yeah, let's say hello to the Power 9 processor. So it was built for the heterogeneous computing, especially sorry. So let's have a look. This is a very high-level picture for the heterogeneous computing on Power 9. So we already have multiple CPU cores on a processor, and they have caches, and they have. Oh, nice. Oh, okay. Give me 1 second. No, it doesn't work. Identify your keyboard. No. Okay. Yeah, it works. Okay. Okay. Sorry for the interrupt. And so what we have done is to extend the on-chip coherent interconnection to off-chip. And on the off-chip coherent interconnection, you can see we have other processors. We call that SMP bus. And we have OpenCAPI devices. Okay, sorry. Those other processors, they also have their own memory subsystem. And we have FPGA or ASIC chips that uses OpenCAPI interface, and they can have their own device memory and a hybrid or storage class memory. And we also have NVLink to connect the GPU and the GPU memory. You will see that all above the on-chip and off-chip interconnections, they are all kinds of processors or processing elements that can do the computation. And on the below, there are all kinds of memory. And our hope or our design purpose is to make the hybrid system that all of the processing elements can access all of the memory system in virtual shared global memory style. So actually, I'd like to introduce AXON. Power Axon is the abbreviation for those interfaces. A means A bus, X means X bus, O means OpenCAPI, and N means NVLink. Okay. So today I will go to the OpenCAPI's style. So OpenCAPI, actually, the OC-Accel logic, it is a bridge on the FPGA FPGA chip, and it interfaces with the action functional unit, AFU, and talk to the software threads through OpenCAPI. So both the blue blocks, no matter CPU core or acceleration unit, can use the virtual address. I mean the 64 bits of virtual address to access the host memory. And also the cache. That's why it is called cache coherence, because it is a cache L1, L2, L3 plus the external DDR memory interface. It is a memory subsystem. And yeah. Okay, so let's look closer about the OpenCAPI Acceleration Framework. Today, above the serial link line, it is the logic inside the host processor, and below this line, it is OpenCAPI device. So to make it as an OpenCAPI device, we need several layers: physical layers, data link layers, transportation layers, and we also have added OC-Accel bridge. And then it is user's function AFU. So today, the three PHY, DL and TL are already open source. They were announced as open source on August OpenPOWER Summit in San Diego. And now on the Europe Summit, we also announced that the OC-Accel is also open source. So what does OC-Accel include? It has the hardware logic to hide all of the details of OpenCAPI transaction layer. So if you have downloaded the OpenCAPI transaction layer specification, you will see that the protocol is not very easy to handle, but OC-Accel translates it to the industry standard AMBA bus XE4. And it also has a software library, user library, to talk to liboc-Accel and provide you some very simple functions to open the device, attach the action, and access the registers and so on. It also has all of the scripts and the strategies to construct a FPGA project. So for the people who had worked on Snap 2, they will find, okay, all of the scripts have been simplified and make it more clear to manipulate an FPGA project. And you can use Vivado GUI in this framework and to build the FPGA image and adjust the timing, the implementation, the placement and the routing and everything in Vivado GUI. So it already supports that. Another thing is the simulation environment with OpenCAPI simulation engine. This feature, we already had that in Snap 2. At that time, it was called PSL-SE, PSL Simulation Engine. So for OpenCAPI, it is called OC-SE. And it also have the workflow for coding, debugging, implementation, and deploying. So have some Python scripts. You can run one command to go from the very beginning to the end. And it also supports high-level synthesis. It uses Xilinx Vivado tool high-level synthesis, so you still can write the C++ code and convert it to Verilog hardware design. And it also has some very simple examples and documents to help you get started. And another good feature is, since on last page, you will see that all those blocks are open source now. So that means it opened to all kinds of new devices, new FPGA boards. No matter you are Kintex UltraScale or Vertex UltraScale, and think about that. The effort is just to move the FPGA project from one FPGA chip to the other. So, yeah. So this is the the overall picture about OC-Accel. So you will see this is the hardware side and the software side. So for the software side, we have the kernel module called OC-Accel. It is already included in all kinds of Linux distribution and a user level libc-Accel. And then it is the OSNAP library. And on the hardware side, we have a bridge module. It includes the TRX and DRX. And actually, it also has the PHY. I didn't draw it here. And it has the data bridge and MMO path and configuration subsystem and some other small modules. So your AFU logic, I mean the action logic, just have some simple interface for configuration and for data transportation. So for the data, for the configuration, it usually connects to some registers. You use some simple APIs to write and read those registers. And for the data path, you are using the 64-bit virtual address to ask for the content of host memory. And on the right side, it is users' choice to enable all kinds of external I/O, like DDR memory controller. And today with VU33P and VU37P FPGAs, you also have HBM. And for most of the cards, you have Ethernet port. So, all right. Okay, so for the new FPGA card support, we have a sub-module. So it has a directory named board support packages. So today it supports 3 cards, alpha data, but they are all alpha data cards, alpha data 9v3, 9h3, and 9h7. So maybe it is a little detailed. So it has some constraint files and Verilog files and the specific IP files for that FPGA type. Okay, so have a little look. Have a look at the workflow. So from preparing the environment, then you start to develop your software and hardware. So for hardware, you have 2 choices about the Verilog and HRS. And then you do co-simulation. And then you build FPGA image. And after you got the bit stream, you deploy it on the FPGA card on a Power9 server, and you can verify how it works. So we have a Python script to go the whole workflow, and if you use help, you can see the choices and parameters. Okay, so for Verilog developers, I'd like to introduce a little bit more about the XC4 memory mapped interface. So this register configuration interface, it is almost the same, no change compared to SNAP2. But this interface, we have supported more features, including, so the most change you should be aware of, especially for the people who had worked on CAPI Snap, is that we have changed the data width from 512 bits to 1024 bits. But don't worry, if you still want to keep 512 bits, you can. We provided the choice. In the framework will automatically insert a DVIS converter. That means data width converter to convert the original 512 to 1024. But you should also pay attention to that. In that case, you cannot fully utilize the bandwidth because you only use half of the data width. And another thing is that we have supported all of the narrow size transfers. We have supported all of the unaligned address. That means This actually takes a lot of efforts from my team, and together with right strobe. That means from some complicated data structure, you don't have to worry about the unaligned address, narrow transfer, and the right strobes. The interface already supports them. So you just follow the AXI protocol, and I believe that can help to simplify your logic design. You don't need to pack your data or split your data, and so you just naturally use the AXI interface. I think that is a good news for some developers. Okay, so besides, we also support AXI IDs. AXI ID means the channels. So if you have multiple engines, for example, if you have 8 engines to working together, so each engine are independent. So you just need to maintain the order of data transfer within this channel, but you don't need to care about the orders among different channels. So in this case, the IDs can help. So today we support at most 32 IDs. But if you want more IDs, the logic size of snap call is larger. So you can choose the number of IDs based on your requirement. For example, if you don't need so many engines, you can just set 1 bit, and it takes the smallest size. And if you need if you have to have more, then you have to consider about this. And another thing is about the multiple process support. So actually, in many modern accelerator design, multiple process is very important, especially think about a database. You have to support many users to query your acceleration engine, right? But those users are coming from different processes or the process contexts. CAPI and OpenCAPI, actually, they support it. So our bridge, our OC-Accel bridge, also have to support it. But I must say that today it is not in the GitHub yet. Hopefully, we can verify the example and open it maybe in 1 month. So it is just under development today. Okay, and so for HRS developers, you just need to write a C function with several parameters. So we will abstract the memory interface as an array. So you write and read this array, so actually you operate the data in host memory. And there is also interface on the DDR memory, and also action register. So action registers, so let me see. Okay, so D in GMEM and D out GMEM, they correspond to the AXI4 master interface. The DDR interface corresponding to the DDR interface, and the action registers is linked to the configuration parts. All right, so let's have a look of how does software and the hardware working together. So for Verilog design, so we start from the main function on software, and it has to include libosnap, okay? And so the open device and prepare the data and prepare what you are going to do, and you attach action. So in this tab, you tell the hardware what is the job you want to do, and attach the action ID or action type. And then you can use all kinds of register access methods to write some control register or read some status register. And today, the interrupt function is also supported. So you can either to keep reading the status register to pulling whether the action has been done, or you can wait for an interrupt. You have to set an interrupt handler and which will be triggered when the interrupt comes back. Okay, and after everything done, the close device and clean up. So this is for the Verilog action. So it heavily relies on the register interactions. Okay, and for HLS, we have already defined internal data structure, means job type. It has some control information and also some parameter information. So when you try to link the HLS action, it is even simpler. You just need to fill the data structure here. It has already a table predefined for you, and then just call the FPGA function directly, and everything will be handled by the framework. But in this case, there may be also some limitations. So it is not as flexible as Verilog design, from my own experience. That is because we have some predefined format, and you have to follow. Okay, and next page. So yeah, this is the simulation environment. So how does the simulation work? Actually, it has, so when you are working, so on the development environment, you have to start three processes. Okay, not three. If you have multiple processes, maybe more than three. But let's talk about the simplest situation, that is only one process, okay? So the first thing is you have to start the simulator. And it can either be XSIM or XClim or iRun from Cadence. And you can also try to add support for other simulators like ModelSim or VCS. And so we have left the script open for that. And the second process is to start is OC-Accel. OC-Accel, you see it on this side, it has a Verilog 2C DPI, yeah, and on this side it connects to the software process from a socket. Okay, so the third thing is to start the application. So it has a So it emulates the feeling that you are running some real software on Power9 server, but at this time, the hardware logic is running in simulator. So with OC-Accel, the simulation, you can verify the correctness of your implementations. That is very important because, you know, if you go to FPGA hardware and you meet some errors, it is not easy to debug. You have to insert some ILA, I mean internal logic analyzer, and you have to rebuild sometimes, and maybe, yeah. So I suggest people to do as much as a simulation before they go to the real hardware. Okay, so together with the GitHub code base, there is also a document website. And so the link for this document is on the first page, README. You can just click on it, and it will introduce the overview and the structure of this repository. And it has a simple user guide about how to, from step 1, 2, 3, 4, 5. And it also has an example tab. Currently, we have just put 4 examples. two Verilog example, one VHDL example, one Verilog example, and two HRC examples. And there is also a deep dive. So it shows all of the hardware hierarchy diagram and also all of the software registers definition and how the OpenCAPI device memory has been mapped. The address layout will be shown in the deep dive. Okay, so some number about the bandwidth. Actually, I didn't update. So today the bandwidth can get to 22 gigabytes per second in the best case. And for the duplex, that means we have 18 for read and 18 for write at the same time. So for most of the user cases, these numbers are, I think, are pretty good. So because on Snap 2, the number from host to FPGA, I think it is a little less than 14 gigabytes per second. So it has increased quite some. Okay, and about the latency. So we measure latency in this way. So here, because this is an AXI interface, so we send the AXI commands from here, and we get the data or response, and go through all of the link and go to the host memory subsystem, and we go back and get it here. We measure, we have some timers, I mean, the counters in this logic to measure how many cycles have it spent to get the response back. So in this case, we make sure that the data we want to access has been prefetched. That means we don't measure the case when a TLB is missed. Okay, so if the data is hit in cache, we can get the best latency is for read it is a little less than 500 nanoseconds, and for write is about 450. And actually this number is about 100 to 150 more than the situation without the snap call. So if you are looking for the extreme short latency, you should try to program something directly on TRX interface. I will guarantee that in that case, if you measure the latency from this point to this point, now it is about 300 nanoseconds. This number is really fantastic. Actually, I believe that today in industry, this is a really competitive number, and no other system vendors have been done that yet. All right, so some ideas about fully utilized OpenCAPI. I think many people had already think about that. The first thing is to ask software thread and hardware thread to work closely to share memory. So think about the paradigm that I had shown for heterogeneous computing. Yeah, so the data is there, and we want to share the data. So talking about this, sorry, sometimes it doesn't work. Okay, I will go here. Okay, so this actually is important. It is a topic about software and hardware partition issue. I think I have already heard some very good practice in this morning and in the presentations before this one. So the basic idea is to do some profiling. There are a lot of profiling tools today on Linux or on Mac or on Windows, and you try, it can analyze the code statically or dynamically, and to analyze what is the hotspot function, and you can then analyze whether it is computation bound or it is memory access bound, and make some decision or try to make some trade-offs about what function are you going to move to FPGA. Okay, so actually this picture is a diagram that from H.265, that is the video encoder, and we try to find out some functions in the motion estimation module and try to accelerate those small functions. Another important feature we should keep in mind is that with CAPI or OpenCAPI, we are able to access the very scattered memory locations. Because you know modern software, they are written in they would like to use many pointers. They are using the list trains or the graphs. They are all pointers from this place to the other place. OpenCAPI can easily handle that because it can use the virtual address. It directly uses the pointers to access the data. And so especially, when we support unaligned address, we support any size of data, we support the byte enable the write strip. That means you can freely use these pointers in a very flexible way. Okay, and next thing is to think about software and hardware working together. So you can simply CPU says start, and all the following thing is FPGA's work. In this case, you offload CPU. That means the precious CPU threads, the cores, they can be used in other places. Okay, but if you want to solve some heavy computation problems, you need to think about the CPU and FPGA working in pipeline. Because OpenCAPI can provide a short overhead to interact between software and hardware, you can get a quite good acceleration if you tune the pipeline very well. Okay, and another thing that we have talked more and more is about to moving data between FPGA and GPU. And I didn't draw another picture here, is that you can also consider sharing data between multiple FPGAs. Because when your logic gets more and more complicated, you may not be able to put all of the computations logic into one FPGA. If you want two FPGAs to work together, and so sharing memory, the feature can help a lot. And so we had some examples. Bruno had and his team had worked on that. That means on Power9 system, the unified memory today, it includes the host memory and also the GPU memory. That means the memory on GPU's side. So for FPGA, it has two choices. It can, so let me say it in this way. So the first choice is that the GPU and FPGA, one uses OpenCAPI and one uses NVLink. They both access the host memory, okay? And another story is that when GPU has its own, so we ask CUDA to allocate some memory in GPU device, GPU memory. It also has a pointer, right? And you tell the pointer to FPGA, and FPGA can directly go to GPU device memory. So this scenario can work for some AI acceleration when GPU is doing some training work, but it also needs some helper to manipulate, to reformat or manipulate the data, like for example, to the video camera, the video stream comes in, you need to mix them together or do some image arguments, or for some data input, maybe you have to decompress it or decrypt it or anything. So in this case, it will be very convenient that the FPGA directly access GPU memory. So it greatly offloads CPU in this case. So the last example I want to show here is about the Ethernet. So because the reason is very simple, because the bandwidth just matches. So we have two ports of 100 gigabits Ethernet, and we also have 20 BPS by 8, so 200 and 200. So they just match. So you will not meet a bottleneck. So this is the conclusion about the OpenCAPI acceleration work. It enables global memory sharing, open, easy development, open, yeah, and it also enables the full throughput and a good latency, so that can help accelerate your function design. So take it now. So this is the address, github.com, OpenCAPI, and OC-Accel. I suggest you to create a fork and so make your own development, and if you think you would like to push it into the central GitHub version, and just create a pull request. And also welcome to create issues and to my team, and we are really glad to have such kind of collaboration together with you. So what's next? Okay, so in near term, I mean before the end of this year, we are going to support multiple processes. We are going to provide a 512 context example to support multiple processes, and it will also has a job manager to handle those processes. And we are also going to enable partial reconfiguration. And we also have an ODMA design here that equals to XDMA. That means your original PCIe-based functional unit that talks to XDMA, you can replace it with the same framework, but now it calls ODMA. The interfaces are the same. And the last one, and which made me most excited, is maybe in early next year we are going to support the home agent memory controller. So what is this? So as I talked for maybe 30 minutes, we are talking about the C1 mode. C1 mode, that means the accelerator is able to access the cache and the memory subsystem, right, as the yellow arrows show. But another capability that OpenCAPI provides is to is that you can extend your device memory to the whole memory map. We call that M1 mode. Okay, so actually these two modes can work together, and they will be our next working target, and to create such kind of thing. That means your software threads can directly push data into FPGA development directly. You don't need a DMA mover to move the data. And this device memory will be mapped into the whole 64-bit memory address as a part. And you use load store instructions to touch that. Okay, so that's all for my presentation, and thank you. And proceed.